Hi everyone, my name is Celestine Okoye. Today we're going to be looking at Heisenberg uncertainty principle. Now, most of us have heard about the Heisenberg uncertainty principle and find it quite interesting, even though it leaves some of us uncertain about how the principle works. Of course, it's a very tricky idea to wrap your head around. So in this class, I am going to explain the Heisenberg uncertainty principle and make it clear to you the best possible way I can. Do not worry, you do not need any advanced level of physics or mathematics to understand this basic principle. Now, what you basically need is just the foundation knowledge of physics and mathematics. In the outline for today's class, we have position. We're going to relate position in terms of physics. We have momentum, which I believe most of you know about, even though I'll still talk about it. Introduction to Heisenberg uncertainty principle. Then momentum and position. We are going to generate or look at the relationship between momentum and position. Then we'll relate the Heisenberg uncertainty principle to energy and time. Then we'll look at some solved mathematical problems. Then I leave you guys with assignment. Let us look at position. Now, generally, we define position or we know position as the location or a place that a particle, an object, or a body occupies or is situated. Now, we have a slightly different definition in physics. Now, when defining position in physics, you must look at a frame of reference or an observer. Now, in physics, we define position as the location of a particle with reference to an observer. Now, a particle at point X observed from a point A has different distance and direction when observed from point B. Now, this means that position is viewed in terms of frame of reference, origin, or coordinate system. Now, if a person is at point A, another person is at point B, which means they are not at the same position, then they observe a particle at point X somewhere ahead of them. Now, it means that the coordinate system of observer A and observer B is definitely different, which means the distance from observer A to the position X and the distance from observer B to the position S are quite different. This means that their coordinate system also in terms of axis will be slightly different. Now, position has a direction, thus it makes it a vector quantity. It has a unit as meter, which means if you look at position in terms of coordinate system from observer A to the point where the position or where the object is located, it means that we can measure that position from observer A to the point of the location in terms of meters, which makes it a vector quantity because it now carries direction. Momentum. We are denoting momentum using the letter P. Momentum is the property of a moving body. Now, it basically tells us that a body that is moving carries momentum, because momentum is the product, the result of multiplying the mass of the body and the velocity of that body, which means a body that is not moving does not have what? Momentum. Momentum is directly related to a particle's speed or velocity. They are different, yes, but in this class, we are going to be using them interchangeably because basically we are looking at the velocity of a body. Momentum is the product of mass and what? Velocity. The unit of momentum is kilogram meters per second, kg ms raised to power minus 1, or Newton second. Now, the Newton second can be derived from the uncertainty principle. When you make momentum subject of the formula from the uncertainty principle, we can derive Newton second as the unit for momentum. Of course, we know momentum is a vector quantity because it carries direction. Introduction to Heisenberg uncertainty principle. Now, the Heisenberg uncertainty principle works within the framework of quantum mechanics, which, by the way, deals with very, very small objects. Now, in the year 1927, Werner Heisenberg, a German physicist, gave that we cannot accurately measure two parameters, momentum and position, at the same time. It is impossible to know the momentum of a body and the position of the same body at the same time. We cannot get them simultaneously. Now, it means that the more accurately you get the momentum of a body, the less accurately you get what? The position of that body. Let us take electrons, for example. Electrons move at a very, very high speed, at approximately the speed of light, which is about 300 million meters in 1 second. We cannot exactly know the position of an electron as well as know the momentum of the same electron. The Heisenberg uncertainty principle states that it is not possible to get an exact measurement of both the position and momentum of an atomic particle at the same time. Now, this basically tells us that there is a limit to how much we can know about some quantities, especially momentum and what? Position. Momentum and position. Now, the uncertainty is basically how uncertain we are about the measurements. Now, remember that we are using the letter X to denote position and we are using the letter P to denote momentum. Given that the change in X is the uncertainty in measuring X and change in P is the uncertainty in measuring P, this means that the product of these two must be equal to or greater than what? Planck's constant. Now, mathematically, we can see that change in X, which represents the uncertainty in measuring X, multiplied by change in P, which is the uncertainty in measuring P, is greater than or equal to Planck's constant. From equation 2, let's remember that P, which represents momentum, is equal to mass times velocity, mv. Now, from equation 3, we see that we have replaced P using mv, which represents mass times velocity. Thus, we have that change in X multiplied by change into bracket mass times velocity is greater than or equal to h, which we have here as equation 3. Now, from equation 4, we can actually understand Heisenberg uncertainty principle even better. Now, look at this. We have change in X greater than or equal to h over change in P, which basically means that from equation 3 or from equation 1, we have made change in X the subject of the formula. Now, basically, remember the way I always say it, that if we have A directly proportional to B, it means that whatever happens to A affects B in the same way. Now, A directly proportional to B means that if we increase A, B also increases. If we decrease A, B will decrease. Now, from equation 4 again, we have that change in X is greater than or equal to h over Planck's constant, which means if we break this equation into phases, we can have that change in X is greater than or equal to 1 over change in P multiplied by Planck's constant. Still, for equation 4, where we have change in P as the subject of the formula, now change in P represents momentum. That's the uncertainty in measuring momentum. Now, from this equation here, we have that if we can accurately know more precisely the momentum of a particle, then it means that we less accurately know the position of that particle, because this equation here represents that change in P is greater than or equal to 1 over change in X multiplied by h, which means change in P is inversely proportional to change in X. Now, let's go back to equation 1. Change in X is the uncertainty in measuring position, which means we do not actually know the position, but we can have a range of positions, which means we are certain about the position. Then change in P represents that we do not exactly know the momentum of a particle, but we can have a range, let's say from this to this. We can have a range of momentum which we have. So the product of the two uncertainties is greater than or equal to h. If you must know also, h is Planck's constant, which is about 6.63 times 10 to the power minus 34 joule seconds. So in the classical world, or in classical physics, where we deal with big stuff, we can practically know the exact position of a particle. We can practically know the exact momentum of a particle. But in quantum mechanics, where we deal with very, very small stuff that are moving really, really fast, we can only deal with probabilities or a range of locations for these particles that are moving. Similarly, in the measurement of energy at a particular time t, we can also apply the Heisenberg uncertainty principle. Now, it follows that change in E is the uncertainty in measuring E, and change in t is the uncertainty in measuring t, then their product is equal to or greater than Planck's constant, which means that the more precisely we get the energy of a particle, the less precisely we get the time which this particle's energy is measured. Now, the product of the two of them is greater than or equal to Planck's constant. Now, from this last equation here, now we can see that change in E is inversely proportional to change in T, which means as we get to know change in E, we get less information about changing T. The same holds here. If we get to know the time, the less precisely we get to know the energy. Now let's look at some problems under Heisenberg uncertainty principle. Now we have about 3 problems that we are going to look at together. Okay, then I'll leave you with assignments. Now, the first one, given that the uncertainty in measuring the position x of a particle is 5 times 10 to the power minus 10 meters, the uncertainty in measuring the momentum is dash. Now we're provided with h, Planck's constant, equals 6.6 times 10 to the power minus 34 joule second. Now the first thing we are supposed to do here is to get the right equation to use, which I believe is change in x multiplied by change in p must be greater than or equals to h. We know some parameters are given. H is given, change in x, which represents the position of the particle, the uncertain position of the particle, which represents 5 times 10 to the power minus 10 meters. So if we put this into this equation, h equals 6.6 times 10 to the power minus 34. Please, this is 10 to the power minus 34 all over 5 times 10 raised to the power minus 10 meters. Please, that represents 5 times 10 to the power minus 10. Now, when we do this, we get our final answer for the uncertainty in measuring P to represent to be what? 1.32 times 10 to the power minus 24 Newton second. So, the uncertainty in measuring the momentum of this particle is greater than or equal to 1.32 times 10 to the power minus 24 Newton second. Now look at the answer we have gotten and this symbol we have used. Now this is to even tell you that we are uncertain about the momentum of the particle. If we are certain, the answer would have been equal to, but now it is greater than or equal to, which means we are uncertain about the momentum.